And now it's recording. Okay. Let me share my screen with you. Okay. Okay, perfect. And okay, it's the fourth class. Okay. So so today we need to talk about some of the measurements and some techniques that could help us a lot to describe and identify some processes that could occur in paleosols. Okay, and the last class we discussed how micromorphological analysis could help us to understand some process. So we saw how some pedofeatures could express concentration or depletion of iron, manganese, silicon, how some pedofeatures could express migration of clay, or even some shrinking and swelling process, and how could voids help us a lot to understand about the activity of clays and some process that could express influence of groundwater, tidal water, or even flooded horizon, or even whole soil. Today, we saw how some chemical analysis could express these influences, and we specifically analysis how the total content of elements could express this results, could express this process that we could saw in paleosols and even in modern soils. Okay. So why analysis of the chemical distribution? Oh, I'm sorry, I did not understand. Okay, stop it. Okay, just check. Now it's closed. Okay. So why analysis of the chemical distribution in the soil could be important? It's quite easy to answer this question. It's because all soil processes that we could think, we could note, we could list, all of them have chemical responses. So all of them influence the chemical composition and the chemical distribution of the horizons, layers, and soil. So if we think in migration of clays and clay minerals, they influence the chemical composition. If we think in the concentration of some elements by variation of EH, we are talking about a chemical distribution or a chemical variation of the composition. So all of them are expressed or could be expressed by the chemical composition and the chemical distribution in a horizon, layer, or even in all soil profile. Okay. Beyond the soil process, the diagenesis also influence the chemical distribution and the chemical composition of the soil, because diagenesis could alter, could modify some minerals and could enrich some materials, especially in silicon, potassium, magnesium, and several other elements. So even after a burial, even after the burial of a horizon layer or several horizons, several layers in soil, specifically a soil profile, we could change its composition. And it's one of the most difficult things that we have is differ the chemical composition and the process that act before a burial process and those that was affected after the boreal stage. So what is the chemical composition of the soil process, and what is the chemical composition that was affected by diagenesis, by the pressure of some sediments, materials, or even other soil above a boreal soil? Okay, this is the most difficult thing that we have, but could be done very easily if we could see the right chemical elements in the right way. Okay, so the first question that we have is which elements we should analyze to understand the chemical distribution, which elements we should think to understand how some soil process and how diagenesis affect that soil. Could you suggest me some, or even just one? And of course, say why some specific element could be useful to us to understand a specific soil process or understand how diagenesis affect that soil?
I think iron, aluminum can be this
Yes, yes, but why you think that iron could be very useful, very important to us?
because with iron and aluminum, it's possible to understand about the uh, which process um, uh, the kind of process the soil is happening. Okay.
Okay, okay. So iron, aluminum, they could express some soil process, yes, especially those process that was affected by age and could express variation of redoxymorphic features. So if you are producing a depletion of iron or concentration of iron, you can analyze and identify that. Aluminum could be also be very important because aluminum did not suffer this process of redoxymorphic alteration, but aluminum could be related to other soil process that affect the aluminum distribution. We could talk specifically about aluminum in the next slides. Okay, someone could suggest other element.
Mm, um, I I don't know. Don't remember.
Okay, okay. So we see, we see. The primary thing that we need to understand is that analyze the chemical composition of soils, horizons, and layers should not be done using all the materials that you have in the soil, because all those materials express different fractions and different process. As we said, when we talk about micromorphological analysis, the coarse and fine grains, the coarse and fine fractions, they express different materials. These coarse materials, gravels, coarse, sand, and even silt, they usually express the influence of the parent material. So if I analyze specifically the coarse fraction and sand and silt, I could understand, I could describe, I could identify the parent material of that horizon, layer, or even all the soil. It's quite important to understand that, because if I analyze only the sand fraction, I could identify the parent material. Why? We all know that sand, it's produced by physical weathering, and physical weathering did not change, did not modify the chemical composition of the material. So the sand chemical composition express the chemical composition of the parent material directly. So it's quite useful to us to identify it. Of course, we have several minerals that compose these fractions, and they are fastly wafered, like olivines, pyroxene, and even feldspars. They could be easily wafered, and so the chemical composition of this coarse fraction, of the sand fraction, could be altered, could be modified by weathering. But if we analyze the right elements, we could understand how the coarse fraction, the sand fraction, express the parent material. Okay? And the choosing of the right element, it's quite related to those elements and its behavior, its chemical composition, its chemical behavior. Okay? For example, we have some elements like zirconium, titanium, and thorium that are concentrated during or through leaching, because the leaching, the wafering, did not alter, did not modify, did not achieve those minerals that are composed or have the highest concentrations of those elements. So ilmenite, zircon, and other minerals which host the highest proportion of these elements, they did not were altered, they did not are wafered by the weathering. In the other way, we have several elements that are fastly leached. So we could understand that some elements, they are concentrated in the coarse material, in the coarse fraction, and those and the other elements are fastly wafered. If we understand this difference of behavior, we could use this difference of behavior to understand how could I identify the parent material, and how could I identify the level, the degree of weathering of that horizon of that material. But we only should analyze these elements to see these answers only in the coarse fraction, only in the coarse grains, only in gravels, or the sand fraction or silt fraction. If we analyze all the soil, we have several problems, and we talk about them in the next slides. Okay? So how could we identify these partners? How could we use the information that we could assess in the lab to understand or to identify the parent material and identify some process? If we calculate the ratio between some immobile and mobile elements, like for example zirconium and sodium, we could understand the weathering and leaching intensity. Because sodium, they usually express they usually are or compose feldspars in the coarse materials. Again, we are talking here in this slide about the coarse fraction, about the sand fraction, silt fraction, and gravels. So sodium, it's only identified on some primary minerals like plagioclase and feldspars. So if I calculate a ratio between an immobile and mobile element, I could understand the level or the degree of weathering of the coarse fraction. And I could understand if the level, the degree of the weathering and leaching, it's high or low. So I can understand, okay, this horizon, I can easily see a high degree of weathering, and here I can see a low level, a low degree of weathering, okay? So if I analyze the level, the content of zirconium and sodium in each horizon, or if I could do better in systematic samples collected by each 10 centimeters or 5 centimeters or even 2 centimeters, I could understand very well the level or the degree of weathering of the coarse material. Let me show you. Oh, I'm sorry. It's just, I should show just one. Just, let me just correct this just a moment. Oh, the animation. Okay, let me just change something. Okay, now I think that will work. Okay, okay. Perfect. Okay, perfect. So let me come back and share my screen with you again. Just a minute. Okay, perfect. Now I need, okay. So we can see in this graph that each 10 centimeters, I'm sorry, each 5 centimeters, I collect a sample and analyze the content of zirconium and sodium, and I calculate the ratio between these elements from the surface to the bottom of the soil. So each dot here express no content of zirconium and sodium, but a ratio between the content of these elements, okay? So we can see very easily here that we have high values here in the top of the soil, in the surface, and this value, the ratio is decreasing. And the ratio is decreasing because the zirconium content is increasing, or I'm sorry, the zirconium content is decreasing, or the sodium content is increasing. Which of these partners, or which of these answers of these possibilities is more useful? The increase of sodium, because zirconium, it's only alters if we have a change of parent material. So the decrease or increase of zirconium content, it's only related to a variation of parent material. But the sodium content in the coarse fraction express the weathering. So if we see in the surface higher values and the decreasing of the ratio, this expressed to us that the content of sodium is higher here than in the surface. So the level, the degree of weathering here, it's lower than in the surface. That's quite easy to understand because here we have materials that are less weathered and leached than in the surface, because here we have gravity, we have plants, we have animals that use the sodium, and of course we have the leaching of these elements here. So we have the weathering in a highest stage in the surface, and the weathering in a lower stage in subsurface, okay? But here we have abrupt, clear variation of the values, because after this decrease of the ratio increase again, and after that has a oscillation, a variation, and a slightly decrease again. Which information could we see using this graph? That here in this graph, we have an abrupt variation of weathering and leaching, okay? And how could we interpret, how could we analyze this information? Could you help me? How could I explain this abrupt, this high variation of weathering and leaching between this phase and this phase in the same soil profile?
Teacher, I think I understand this. This graph is with the more deep um, uh, we have conditions with weathering and the leaching, but we have with a moment more um, stability. We have a condition more stable. That's
Okay,
okay.
okay. I'm not sure. I think that Mm, uh, depends on what you are talking about stability, tectonic
Mm.
stability or chemical stability. I need to understand better what you are talking about in this case and what you are talking
It's
about stability.
stability through relation with um, um, change, no, chemical changes. Um,
Mhm.
the transformation,
Okay,
chemical.
okay. Okay. Oh, the information that's it's fast, the easiest to understand is that we have here on stage, and here we have other stage. So here we have several horizons or layers, and here we have other horizons and layers that have different behavior of weathering and leaching. Okay, is the first information that we could extract from this graph. Okay, so now we need to think which process could explain this variation of weathering, of leaching. So we have several soil processes and several geomorphological processes that could express this variation. But the most common is the burial of soils. If we think that in the past we have a soil that's been weathered, it's been weathering and leaching, and of course in the surface we have a higher leaching and weathering. In the subsurface, we have lower levels of weathering and leaching. But after a boreal stage, we have a new material, a youngest material, overlying this older soil. And now the weathering in the boreal soil stops or achieve a lowest level. It's very, very low because now we don't have so much migration of water. Now the voids could be lower, or the soil could be denser because the pressure of the overlying horizons and layers above this buried soil. So the weathering in this buried soil stops, okay, or achieve the lowest levels. And now the weathering only occurs in this overlying horizons and layers in the new soil, okay? So here, this variation could express us in the most common of the cases that here, this phase express a buried soil, and this phase express overlying horizons and layers that buried this soil. And it's because we have this variation of weathering and leaching intensity or degree. Because here we have the surface of this newest soil, and here we have the subsurface horizons and layers of this overlying horizon. And here we have the buried soil, the surface horizon that in the past suffer too much or a higher degree of weathering and leaching than the subsurface horizons. Okay, so this abrupt variation of weathering and leaching could express a burial process, because we have a abrupt variation of weathering, and the weathering could express the proximity, the near, the closest to the surface. And this abrupt variation could express this. It could express, as you said, variation of chemical or physical process too. For example, we could have stage or intense weathering in specific horizons and layers in specific depth, like here. And here we have a specific soil process that did not favor the chemical weathering, like we have some stone line, or we have some specific material, some specific mineralogy that could or could not favor the weathering. And it's because the weathering is highest or lowest, okay? So this variation could express some materials that could be related here, okay, could express this high variation in the ratio between these elements, but we usually found this high variation in buried soils, okay, because the coarse fraction of these buried soils express a high weathering in the surface horizons, and the weathering of the surface horizon is quite higher than the subsurface horizon of this newest soil, okay? These newest layers or horizons that overlie in the buried soil. Everyone could understand that? Is everyone, or we have any doubt about that? Or how could
No,
we use? Okay,
That's okay.
I have some questions, Professor.
okay, okay.
First, I have a doubt about how can we actually know that this is that we are talking about a paleosoil,
Mhm.
because this change, this abrupt change in the ratio could be because due to a change in geology or
Yes.
some rock. And the other question is the this pattern of having a high ratio in surface and a less a less ratio in subsurface is a pattern in all soil or no, or can be different
Okay.
some kind
O-
of soil.
Okay, okay, Johanna. The first question, how could we know that this is a paleosol? Okay, only this data could not say this to you, okay, because we need to use other information like the morphological description in the field, okay, because it could express a modern soil too. So
Mhm.
only this graph, only this data could not say to you, okay, this is a paleosol, okay? You need to merge this information, this data with other data that you collect in the field and in the lab, okay? So don't worry, you did not say see this partner or this kind of graph and okay, this is a paleosol. No, could express a modern soil too. You need to merge with other information. Okay.
Okay.
And the second question, it's if we could see this specific partner of decreasing of the ratio according depth. If we have well-drained soils and the climatic and tectonic stability during the formation of that horizons layers of that soil, we have this partner, okay? Because it's typical that feldspars, olivine, pyroxene, biotite, and all of these easily preferred minerals are decreasing its content. So the content of sodium, potassium, calcium, magnesium, and other elements is decreasing in the surface because the leaching and weathering there it's more intense than the subsurface horizons because the subsurface horizon you have less oxygen, you have less migration of water, you have less water, and in some cases you are closest to rock or even the parent material. Okay, so the weathering of the coarse fraction, because you always need to remember we are talking about the coarse materials. The weathering of the coarse materials in the subsurface, it's lower than the surface horizons or layers. Okay.
Okay, I got it. Thanks.
Okay, very good, very good. So if we calculate the ratio between immobile and mobile element, it could express to us the level, the degree of weathering and leaching, and we could see only one phase. We could see only a decreasing of the ratio that express that we have different states of weathering only according to depth, or could we see something like this that's more interesting because could express us, okay, we have a specific change here, okay, and as I said, in the majority of the cases, in the most cases, it's a buried soil. Okay. But of course, we need to merge this information with other information. Okay. In the field, I saw close to the staff, dark horizon or layer that could be related to a buried surface horizon. Okay, very good. The data is expressing something that I saw in the field. Okay, and beyond the ratio between elements that possess difference of chemical behavior, we also could calculate the ratio between two immobile elements, like, for example, zirconium and titanium. These elements, they did not are easily wafer and leached because, as I said, they compose hardly wafer minerals. And so they express the nature of the parent material. So if I calculate the ratio between two immobile elements, I could understand if those soils or a specific soil, or like in this case, I can see a new soil and a buried soil, if they are related from the same parent material or if they are related to different parent materials. Okay, and it's what I want to show here. We can easily see here a low variation. It's a variation, but it's a low variation between this ratio and zirconium and titanium. But here in the same depth, we could see a high variation between these values, this ratio, and these values. So again, we have a phase here and here another phase. That means that these horizons and layers and these depths, they are related from a specific parent material, and these horizons and layers, they are related to other parent material. Okay, they are related to other parent material. It's not a difference of weathering, but it's a difference of nature. For example, on these horizons and layers, they could be related to basalt, and these horizons and layers, they could be related to a aeolic sandstone. So we are talking about a difference of parent material of these layers. And if I have these two behaviors, these two graphs in the same soil profile, I could understand that this buried material, this buried horizon layers, this buried soil has a specific parent material, and this overlying horizons and layers, this newest soil, is related to other parent material. So I could understand this graph. It's not the same because here I use a difference of values. So you can see that the graph starts at 0 here, and here starts at 10. So we have we need to change, but they are in the same level. So the 0 is here and the 0 is here. Okay, but if we match these graphs, we could see that the difference of weathering could express a difference of parent material too. So we have a paleosol that was buried, and this buried paleosol was derived from a different parent material from this overlying horizon, this specific soil in the surface. Okay? Everyone
Okay.
understand that?
Yes, I have a little doubt
Okay, okay.
about why we are using here zirconium and titanium. What they indicate.
Oh, just because they are immobile elements, but we could use other elements, okay? I love to use these elements because zirconium and titanium, they are, how can I say, they are usually used for identification, to identify differences of parent material. Okay. For example, the WRB, the World Reference Base for Soil Resources, they use zirconium and titanium to identify differences of parent material or left discontinuities. So you could use other elements. Don't worry, I could use war elements. I could use have metals. I could use other elements, but you always should use immobile elements to identify differences of parent material. In some cases, you could use aluminum and iron, okay, because they are related. They are quite mobile, but I did not like to use them because they are also common in easily weathered minerals. For example, olivine, pyroxene. So they usually express more the weathering than differences of parent material. Okay. Okay.
Okay. Uh-huh. Okay.
Okay. And again, people, we are only talking about the chemical composition of the coarse materials, gravels, sand, and silt. Because if I analyze clay fraction is another word. It's other things and it's another interpretation that I have to done. Okay? Okay, perfect. And we could calculate some geochemical indexes of weathering and leaching. Okay, it's quite common in the references and the literature. And actually, I did not like them very much because I saw a lot of problems. So let me present you, and after that, I will say why I did not like them very much. The first one is the most common geochemical index of weathering and leaching is the chemical index of alteration, or only CEI. Okay, it's a ratio that we calculate between aluminum and aluminum plus calcium plus sodium plus potassium. Okay, here we did not use calcium related to carbonates. Okay, only calcium related to silicates, only related to minerals that we have calcium and silicium at the same time, like plagioclase. Okay, and this chemical index alteration is related to weathering of feldspars and plagioclase. So in this case, with that the
Teacher.
weathering, okay,
Oh my gosh. 1 minute. 1 minute. What's the translation on the chemical index alteration and the weathering index of the Parker in Portuguese?
in Portuguese, we call índice de alteração química for the first
Mm.
one,
Mm.
e índice de intemperismo de Parker for the second one. Okay?
Okay. These indexes are a lot used or no in the research in Brazil?
In the soil science, they are usually used. in soil science. We can
Okay.
found easily in some works, some articles in Brazil and even abroad, especially abroad, Brazil. We saw a lot of works of studies that present these indexes. Okay.
Okay.
But as I said, they were born in geology because the geologists they love to use these indexes. But in the soil science, we have some limitations that I will talk about then here. But first, just me present you, and the first one is specifically related to the weathering of feldspars. So we understand that feldspars are the main minerals that we can find in rocks, in the parent materials, and its weathering express the weathering of the parent material. And so if we destroy feldspars, we will lost especially calcium, sodium, and potassium. Okay, so we use the content of aluminum only as a parameter to identify how much calcium, sodium, and potassium were lost by the weathering of feldspars. Okay, and this result, this chemical index alteration, would express the weathering of feldspars, and of course, will express the weathering of the soil. And according to the value of the chemical index alteration, I could understand if the weathering is high or low. Okay, if I have a low value of chemical index alteration, low values express a low weathering, and high values will express high weathering and leaching. Okay, is the very easy way to understand how chemical index alteration could be used. It expressed the weathering of feldspars, and because of that, the leaching of its components that are calcium, sodium, and potassium. And the high values express a high leaching of these elements, and low values express a low leaching of these elements. Okay? Other index that's quite common is the weathering index of Parker. That's only WIP if you want to use only some letters. And here, I'm sorry, here we could calculate another expression according to the molecular weight of each of these oxides. Okay, and here we use sodium, magnesium, potassium, and calcium. Again, we should not use carbonates here, so we should not use calcium related to carbonates to calculate the weathering index of Parker. And using this formula, we could calculate the weathering and leaching of the materials. And the difference between them, of course, are these values that are related to the molecular weight of each of these oxides. But we easily can understand that here we use aluminum, and here we did not use aluminum. Why the weathering index of Parker did not use aluminum? Because here we understand that aluminum is an immobile element, and aluminum did not migrate in the soil or sediment. And all the aluminum is related to feldspars or primary minerals. But we know, and Parker was the first one to say it, aluminum, it's not only in primary minerals, and aluminum is a mobile element. So aluminum could be present in other materials and could be concentrated by some soil process. So even if analyze the chemical composition of soils and horizons, and if I analyze the aluminum content, it could express some variations of soil process and could express some variations that are not only related to weathering. So it's why we did not use aluminum to calculate the weathering here, and only here we use, okay? The chemical index alteration was one of the first chemical indexes alteration that we could use, but today we use it only for comparison, but we understand that it have several limitations, and the most important, it's related to aluminum, because aluminum is an immobile element, okay? But even the weathering index of Parker have problems, and they both have a specific problem that are in common, that is the use of calcium. Because if you are talking about a soil layer or horizon that present carbonates, we can't use these indexes, or you should measure how much calcium is related to carbonates and how much calcium is related to silicates, and only use the content of calcium that's related to silicates that are not related to carbonates. So if you have carbonates in soil or in your horizon or layer, you should avoid use these indexes, or you should individualize how much calcium is related to carbonates and did not use this amount, okay? Because we are talking about only silicates, only minerals that are not very easily dissolved, but could be dissolved in a geological time, okay? Beyond these problems that we have with aluminum here and calcium in the both, we have several problems with the people that use these geochemical indexes. As I said, they were born in the geology, and for them, it's quite easy to understand that, because we are comparing some saprolites, and okay, the saprolite, it's less leached than this one, so okay, it's not a problem. But when we talk about soil, we are talking about several fractions and several processes that could occur. Soils are more complex than rocks. So we could see in several papers, several works, people using all the fractions to calculate the chemical index alteration and the weathering index of Parker. So a lot of people use sand plus silt plus clay. They analyze all these fractions, the free fractions at the same time, and with all this data, they calculate the chemical index alteration or the weathering index of Parker. And of course, we have a lot of problem, because, for example, aluminum in the clay fraction, it's highly mobile, could migrate very easily and fast through the soil profile. So aluminum could migrate, for example, with organic matter and concentrate in spodic horizon. So if I calculate the chemical index alteration if with in a soil that possess a spodic horizon, I should understand that even aluminum migrate, and the aluminum content in each horizon could express a depletion of aluminum or a concentration of aluminum, because aluminum migrates with organic matter. So we have a huge problem with that. Okay, so I did not recommend you to calculate these geochemical indexes using all the fractions. If you really wanna know the degree of weathering and leaching, only use the coarse fraction, only use gravels and silt and sand. Because if you include all of them at the same time, you have a lot of information, and it's quite hard to understand what is going on in your soil, in that horizon or in that layer, okay? And other problem that we have with these indexes is that all of them, it's not only this both, but all of them always think in a progressive leaching. So all of them always think that, okay, we have the crystallization of the material, the crystallization of minerals, rocks, and after that, the weathering starts to occur in a incipient stage, and after that in a moderate stage, and after that in a developed stage, in a intense stage. So all geochemical indexes of weathering, all of them always think that some elements will be leached and some elements could be concentrated. But when we think about paleosols, and even when we think about modern soils, we should think that some soils could be polycycle. So we could have different processes acting, we could express different climate conditions, topographic conditions, and all of these variations could express variations of chemical composition. That's not only weathering and leaching. For example, a variation of chemical composition could express variation of parent material. It's not a variation of weathering and leaching, it's a variation of parent material. And if we calculate these geochemical indexes, they could express a variation of parent material and not the weathering and leaching. So if you ask me now, JJ, could I use these indexes? I'll say, okay, you could use these indexes. Okay, do you like them? No, I did not like them. And I did not use them because I think that they express information that's not so useful to us. They are very useful to compare your specific soil that you are studying with other soil in another area. Like, okay, I'm comparing my soil here in Brazil with a soil that I'm sorry, with a soil that Johanna collected in Antarctica. Okay, but it's really important to compare this. It's really important to understand how they have different stages of weathering. Only this geochemical indexes could express that. The minerals, pH, CEC, morphology. We have a lot of morphological evidences and other chemical evidences that express weathering and several other informations. So these geochemical indexes, they are used, but they did not say anything new to us. And to me, they could bring some problems with them, and they generally do that. And people that use them, they generally think that we have approximative leaching, and they express only weathering and leaching, and people generally use all these diffractions together. So we have a lot of information that have a lot of problem because soils are not so simple. Okay, so again, you will see a lot of studies that use these geochemical indexes, but I personally don't recommend them. You can use, it's not a problem, but I personally do not recommend them. What I recommend to you, use these ratios, because these ratios could express the bulk information to you, and the bulk information could be interpreted in different ways, and you can easily understand how the ratio could variate in these cases, and you are understanding what is going on with your soil. You did not think, okay, I have a progressive leaching and progressive weathering, and it's always going in the specific way. No, okay, but again, you can use these geochemical indexes. Okay. Any doubt about that?
Okay, teacher.
Good.
I would like to know about the other ratios that you recommend, how we obtain the contents of these elements.
Oh, they usually use X-ray fluorescence because you assess the total content of these elements, but you also could ask the digest the samples, and analyze the chemical composition in an ICP or an atomic absorption spectrometer. Okay, so we usually use X-ray fluorescence, but you can use other techniques too. The X-ray, I think that's easiest way to analyze and to measure this chemical compositions. And the X-ray, they access the content of these elements very easily. So even if you have a low content of sodium, you could measure it in an X-ray. Okay, and of course it's faster, and you use less. How can I say? You use less equipments and less simple preparation than acid digestion. Okay.
Okay, it's safer, right?
Yes, yes, safer. You are not using acid, so it's better to environment and better to you.
Yes. Okay.
Okay, now let's think about how could we use the fine fraction to understand some process. The fine fraction could tell us a lot. As you can see, we can use several elements, and each element express on a specific process in a specific case. So if you extract only the clay fraction and analyze only the clay fraction, you could access some informations. And these informations, they usually express the action of the genesis, the pedogenesis of that horizons, layers, and that soil. Okay, but and this is a huge problem to us in paleopedology, is that diagenesis affect the chemical composition of the clay fraction. So the chemical composition of the clay could express the pedogenesis and or diagenesis. And how could we differ between them? It's not easy. It's not easy. We only could differ the action of pedogenesis and diagenesis in the chemical composition of fine fraction using isotopes. And so it's not cheap, but we could compare the isotopic composition of clays and understand, okay, these clays are related to pedogenesis, and these clays are modified or were modified by diagenesis after a boreal stage or something like that. Okay, because the isotopic composition tell us a lot about this process. We did not talk about this in this specific class, but in the next class, we will talk about the use of isotopes, okay? So for now, we have a problem with this, but we can solve this problem. It's not cheap to solve it, but we could solve, okay? And we are talking only about the chemical composition, about this fine fraction, and this could express a lot of information to us. Okay, for example, the aluminum content could express the migration of clays and clay minerals, okay, and could express, for example, the lessivage, the migration of clays and clay minerals from the surface to the subsurface horizon, which produce some clay skins, for example, because aluminum could be hosted inside kaolinites and other silicates. So the migration of kaolinite could modify the chemical composition of aluminum, the distribution of aluminum in the same soil profile. And the migration of kaolinite, of clay from the surface horizon could decrease the content of aluminum in the surface and could enrich or increase the content of aluminum in the subsurface horizon if this horizon is accumulating kaolinite and, of course, aluminum. Okay? And as I said, aluminum also could be migrated in some specific soils, especially sandy soils like podzols or spodossols, or in Portuguese, espodossolos. They all could register migration of aluminum because podzolization. The podzolization is the migration of aluminum oxide with or without organic matter from the surface horizon or an overlying horizon to the spodic horizon, a B horizon that possesses a dark color or a red or yellow color, and this spodic horizon accumulates organic matter and or iron oxide and or aluminum oxide. So if I analyze the chemical composition of horizons and layers, the variation of aluminum content could express these two processes. JJ, how could I differ between them? It's quite easy. It's quite easy because lessivage, the migration of clays and clay minerals, the migration of aluminum inside kaolinite produce clay skins, some shiny surfaces, and podzolization did not produce shine surfaces. And podzolization, generally, they usually are related to sandy soils, okay, or specific cases. So even in paleosols, we could measure this migration, this chemical distribution, and okay, this is an ancient B horizon, argic horizon, or agelic horizon, which concentrate kaolinite because we can easily see an increase of aluminum, okay? Or, okay, in the past, we can see an ancient spodic horizon because we can see easily an increase of aluminum content, okay? Of course, this increase of aluminum content, it's not only evidence that we should use to identify an ancient horizon, but could be very useful to us. The variation of the distribution of silicon in specific soil profile also could express the depletion and migration, because we could register the migration of clays from the surface horizon to the subsurface horizon, or we could measure the destruction of clays and the concentration of amorphous clays or low crystallinity minerals in subsurface horizon, okay? And the variation of distribution could, especially about silicon, could express variation of pH. We all know that high pH induce the destruction of silicate, so clay minerals, they usually are destroyed in high pH like 8 or even 9, and so the depletion of iron will be very high. And if I can found in a second profile low contents of silicon in the surface horizon and high contents of silicon in the subsurface, this could express a variation, an ancient variation of pH. So in the past, we have a high pH in the surface that destroy the the clay minerals, and so silicon migrate from the surface and concentrated in the subsurface, because in the subsurface we have a different pH, we have a lower pH, or even we have a lower porosity. So the migration of silicon is not so easy, and because of that we have a concentration of silicon, and even we could create cemented horizon related to concentration of silicon, okay? So the variation of the silicon content could express as aluminum, the migration of clays and clay minerals, but also could express a variation of pH and or porosity that express a destruction of silicon minerals in some horizons, and the concentration of amorphous or low crystallinity minerals in a specific subsurface horizon, okay? And the content of iron and or manganese, they are usually related to the depletion and concentration of these elements that express each variation. So the variation of iron content could be used to identify paleosols that in the past suffer depletion of iron because they are flooded, for example. In a study in the past, I used a ratio between zirconium and iron to identify paleo horizons that suffer depletion of iron in the past. Because, I'm sorry, zirconium are not depleted in flooded conditions, but iron it's depleted. So the ratio of the clay fraction of zirconium and iron could identify some areas that could be flooded in the past and could be depleted or could lost iron and or manganese in the past. We don't see a lot of studies that use manganese because manganese are not so abundant in areas, so iron express so much better than manganese, but of course we could use manganese too. Okay, so the variation, the bulk variation of iron could express these depletions and concentrations, but we could also use a ratio between an immobile and iron element to express this variation of EH conditions. Okay, we could use they both. Which one should I use, JJ? Those express better this information that you want to say. Okay, so if the iron content in the clay fraction express, good. If it's not expressed, maybe you should use a ratio. And I personally use a ratio, or usually use a ratio, because I understand that we could depletion followed by the concentration. And sometimes this could change the iron content, the bulk iron content. So it's better use an immobile element, or even an immobile element that did not suffer with the EH variation, okay? Calcium, magnesium, and strontium, and they also could be related to depletion and concentration of these elements, and they usually express CO2, or carbon dioxide pressure in the soil. So the variation of content of calcium, magnesium, and strontium could be related to variation of presence or absence and weathering and leaching, precipitation or not of secondary carbonates. So they could be very useful to semi-arid and arid regions. And sometimes they could be related for some salts too. Okay, so of course you need to understand if you are precipitating some chloride or some carbonate. So you need to understand that. We also could measure the content of dioxide carbon or some carbonates in the soil, then could express this variation too. As we said in the class, that we talk about some minerals and how they could express chemical variations. We also could analyze the chemical composition, the chemical distribution of other elements like sulfur, chloride, bromine, and other elements. And I love these three elements because they usually express influence of tidal water. So if I analyze in a soil profile, a specific soil profile, and we can see a huge difference of sulfur content, maybe some of these horizons suffer in the past influence of tidal water, and some of them did not suffer this influence. So help us a lot to understand how the minerals could be very different and how the pH and several other properties of the soil could be different, because we have the influence of tidal water in specific horizons or in a buried horizon or a buried soil. Okay, so if you want to analyze the fine fraction, the clay fraction, we have a lot of methods, we have a lot of elements that could be very useful to understand distribution of soil, but we should understand that each one say on specific case, and they generally are related to specific soil process. So if you want to understand the evolution of that paleosols from the fine fraction, you should study very deeply the process of soil formation, all the process of the soil formation, because these chemical contents will express that. Okay? And as I said, we always need to understand that the chemical composition of the fine fraction, it's fastly changed by diagenesis. And sometimes we only could not differ between the pedogenesis and diagenesis. We should use some specific methods to understand the difference. Only the chemical composition did not say too much for us. Okay? Okay, guys? Or better, girls?
Okay, teacher.
Okay. On this class, I think that's the last slide. Yes, this last slide. Just, is it? Okay. In this class, we just need to talk about how could we use the chemical composition, and I will share a reference with you all about how could we use other elements beyond this that I present here. And please read the material as soon as possible. In the next week, we will talk about how could we use some isotopes to date soil and to identify some specific process. Okay. In the next week will be the last class, and we'll talk about the last topic. And after that, I will share with you some questions, and I will bring you something like 1 or 2 weeks to answer these questions. Okay, so you have 1 or 2 weeks. I will decide according to the number of questions. And after that, you send me for email the questions and I will correct them. Okay. Of course, if you have any doubt about one of these questions during this 2 weeks or 1 week that I will give to you to answer the questions, you can send me an email. And okay, JJ, I need help with this question. How can I answer this, and that? Okay, it's not a problem to me to talk about one of these questions. And they are theoretical and practical questions to interpret, and how can we express and extract information from some specific analysis, and how can we use morphological data to understand how paleosols evolve. Okay, so all the questions we use, all the information, all the maths that we talk in all the class, all the course. Okay. Okay, good.
Professor JJ, will you post a video of the class that you couldn't give us?
No, it's not needed because it's this class. It's this class.
Okay.
Yes. So don't worry.
Okay.
Okay.
And could you send us these questions maybe next week or soon as
Yes.
possible? Because the last week of the year is a little bit difficult.
Yes, I know. But as I said, I will send you, I will bring you something like maybe 1 or 2 weeks. So maybe only you just need to send me the answers like January 4th, something like that. So we will have a huge period to send me. But okay, it's not a problem. I can share all the questions in the next week. It's not a problem. Okay.
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 Thanks.
Okay. No problem. Amanda, your phone is muted. We are not.
Oh my God, teacher. Next class we class.
Could you repeat, please? I did not understand.
Next week we have class.
Yes, but it's the last one. It's the last one.
Okay. Okay.
Okay.
And do you send the questions this week or next week?
I think that's next week because this week I'm very busy. But I will try to share with you maybe before our class. Okay. Maybe in the Monday or Thursday. Okay.
Okay. Okay.
Okay.
Okay.
It's just
Okay.
because I'm going to travel in the last week of the year. And
Okay.
I will
No
try
problem.
to answer before that.
Okay. No problem. No problem. Okay. Okay. And so see you in the next week. And if you have any question, as always, just let me know. Okay. Bye bye, girls.
Bye bye. See you guys.
See you.
Bye bye. See you.